this is John Whitaker for the Analysis 2 class, and this is our 5th video lecture. And we're going to concentrate today on L'Hopital's rule. Before we get to that, we're going to review some information, some definitions primarily, that we saw at the end of Analysis 1, in the very last lecture for Analysis 1. Namely, some definitions about neighborhoods and limits of functions towards infinity or being infinity. So recall the following definitions. Here's one. It says if x is a real number, then a neighborhood of x is, I'll write down this, n sub r of x, which is really equal to the open interval from x minus r to x plus r. It's all the numbers in between x minus r and x plus r. 2. For any real number c, the set of all real numbers x such that x is bigger than c is a neighborhood of infinity, and written as so this will be c to infinity. That's the neighborhood of infinity. Thirdly, the set minus infinity to c, for any real number c, is a neighborhood of minus infinity. So that's what a neighborhood of minus infinity is like. The fourth thing I want to recall is if we let f be a real value function, on E, so it's defined on E, which is a subset of R. We say that f of t goes to A as t goes to x. This can be written as the limit as t goes to x of f of t equals A. Where A and x are elements of real numbers union the set of either plus infinity or minus infinity, if for every neighborhood of A, say, we're going to call those neighborhoods U, there exists a neighborhood V of x such that V intersect E is not empty and such that f of t is an element of U, and that's true for all t elements V intersect E with t being different than x. So that's our definition for this limit. And that's going to be important for L'Hopital. So what is L'Hopital? It's the following. So here's a theorem. L'Hopital rule. Here's what it says. It says suppose F and G are real and differentiable in A to B, and G prime of X is different for 0 for all X element of A to B, where minus infinity is less than or equal to A is less than D, which is less than or equal to infinity. Okay. Suppose also the limit as x goes to A of the derivative of x over the derivative of G, that equals to A. Then we'll have two more possible suppositions. It says if the limit as x goes to A of f of x equals to 0, and the limit as x goes to A of g of x equals to 0, then, well, I should say, or if, part 2, the limit as x goes to A of g of x equals to infinity, then, so here's the conclusion noted state, if either one of those things happens, then the limit as x goes to A of f of x over g of x is also equal to A. So this gives us a way that if we get some kind of indeterminate limit form of 0 over 0, or if the bottom is infinity, and yet the derivative was equal to A, the derivative of the top, the derivative of the bottom is equal to A, so you take the limit as x goes to A, then that will give the limit as x goes to A of f of x over g of x. Okay, so that's the theorem. We want to prove this. And our proof will be based on the Cauchy mean value theorem, which we've proven. And really, I'll do most of the proof here, but I will leave a little bit as it's similar to what I would have done. So there'll be a little bit of an omission. Before I go to the proof, I'll say this. The analogous statement is true if x is going to B, or if, for part 2 of our assumptions, that g of x is going towards minus infinity in part 2. So here's the proof. We let f and g be real and differentiable
g prime of x be different from 0, and that's true for all x in a to b, where, so this is the hypothesis, or at least part of it that I'm assuming, where minus infinity is less than or equal to a, is less than b, is less than or equal to infinity. We're also going to suppose that the limit as x goes to a of f prime of x over g prime of x equals to a. And now we're going to get the conclusion by assuming some cases on what a is. So we're really going to have three cases. So here's case one. If a is equal to minus infinity. Minus infinity. Now, we want to show, under some more hypothesis, we want to show that the limit as x goes to a, really it's from the right, of f of x over g of x is also equal to a, okay, which is equal to minus infinity. So how are we going to do that? Well, we're going to use the definitions that we had up here to start this lecture. I'll use that. Okay, so we're going to let Q be an element of R. We want to show there exists a D element of A to B such that for all X element of A to D, then f of x over g of x will be less than q. So this says that I'm giving you a neighborhood from minus infinity to q of minus infinity. So for each neighborhood, so I'm giving you one. And what I've got to do is find the neighborhood of A, and that's this type of neighborhood. Such that for all x or t, x, then this will happen. Then f of x over g of x will be less than a q. This f of x over g of x will be in the neighborhood of minus infinity. All right, well, what we're going to do is we're going to let r be less than q. So pick a number. We've got a q that's a real number. We pick an r also that's less than q. Well, since the limit as x goes to a of f prime of x over g prime of x equals to a, okay, then, well, this a in this case is minus infinity. Equal to minus infinity. Then, there exists, I'll say a C element from A to B, such that for all x in A to C, f prime of x over g prime of x is less than r. Now, by Cauchy's mean value theorem. For, let me just write this part down. A less than X less than Y less than C. So here we have an X and Y in A to C. There exists a T element, so this is a T, it's an element of the open interval from X to Y, such that f of X minus f of Y over g of X minus g of Y will be equal to f prime of T over g prime of T. But for this fixed T, it's in A to C, okay? And for everything in A to C, f prime of that over g prime of the same thing was less than R. Now, we haven't used all of the hypotheses that are possible, that are available to us in this statement. So in particular, I'm referring to, in the statement, the parts 1 and 2 of the hypothesis, which part 1 said that the limit as x goes to x goes to, or t goes to x, I should say, of, no, it's x goes to a, of f of x equals to 0, and the limit as x goes to a of g of x equals to 0. Let me write that down. Suppose the limit as x goes to a of f of x equals to 0, and the limit as x goes to a of g of x equals to 0. Then, if you look at the limit as x goes to a of f of x minus f of y all over g of x minus g of y. This is going to be equal to, well, here, f of x is going towards 0, g of x is going towards 0. These are constants, so their limits are non-zero. And so what you get, well, their limits are themselves. So you get minus f of y over minus g of y, which equals to f of y over g of y. Now this is going to have to be less than r, where let's say less than or equal to r, where we have a is less than y is less than c. Now, thus, the limit as y goes to a of f of y over g of y is going to be less than or equal to r, which is less than q. And so that is essentially what we wanted to prove. So I'll say, so there exists a D element of A to C such that for all x element from A to D f of x over g of x is less than q. That's what we wanted to show. So that proves the theorem in this case, where a is considered to be minus infinity, and we're assuming part one of the hypothesis. Now, maybe you can call that subcase one. Case one. The other situation is where we assume the hypothesis that the limit as x goes to a of g of x equals to infinity. And so that's what we'll work on next. So here, suppose the limit as x goes to a of g of x equals to infinity. Then, as we had before, we keep keeping y fixed in a less than y less than c. We can pick a point C sub 1 that's an element from a to y such that g of x is greater than g of y and g of x is greater than 0. And that's true for all x element, for all x as an element from a to c sub 1. And this is based on the fact that we know that g of x goes towards infinity. Okay, so we can do these two things. Now, since f of x minus f of y over g of x minus g of y is less than r, and this is going to be true for all x element from a to c sub 1, it's a statement that can be gotten for all x in between a and c sub 1. Then f of x minus f sub y, f of y, I should say, over g of x minus g of y times g of x minus g of y over g of x. So this is going to be less than r times g of x minus g of y all over g of x. And the reason that this is true is because really I'm multiplying both sides of this inequality by a positive number. Okay? So that's what we have. Okay. So, f of x minus f of y all over g of x then will be less than r times, well, one way of writing what we have is g of x over g of x minus g of y over g of x. And so what that says is that f of x minus f of y over g of x is going to be less than, this is 1, so it's r minus r times g of y over g of x. Okay, and so we can break this fraction up and do an addition, I should say. So what we have is f of x over g of x is going to be less than r minus r times g of x, g of y over g of x. And then this will be plus f of y over g of x. So, the limit as x goes to a of f of x over g of x is going to be less than the limit, less than or equal to, the limit of all of this, which will be r minus, the limit as x goes to a of r times g of y over g of x plus the limit as x goes to a of f of y over g of x. Okay, before I go any further, before I leave, look, g of y is a number, and it isn't involved in this limit. We're holding y fixed. R is a number, so this is a number. Now, as x goes to a, g of x is going towards infinity. And so we're taking a number divided by a huge number. That goes towards 0. The same thing's happening here. So, what we have is that the limit as x goes to a of f of x over g of x is less than or equal to r, which is less than q. And so, that means there exists a d element from a to c1, which is going to be good enough, such that for all x element of a to d, f of x over g of x is less than q. And so that says the limit as x goes to a of f of x over g of x is equal to minus infinity. Okay, now that was the working under the case where we considered a to be minus infinity. Now, case 2, what if a is equal to infinity? Okay, we want to show, it's a very similar situation. We want to show, analogous situation, that the limit as x goes to a, really it's from the right, of f of x over g of x is equal to infinity. And what we'll do is we'll say, we'll let w be an element of real numbers. So we need, okay, we want to show that there exists a D element of the open interval from A to B such that f of x over g of x is going to be greater than w, and that's true for all x element from A to D. Well, this role of w is like the role of q that we had before. And so what we're going to do is we're going to let u be bigger than w. Now our u is like our r. So here, since the limit as x goes to a of f prime of x over g prime of x equals to infinity, there exists a C element of the open interval from A to B such that for all x element of A to C, f prime of x over g prime of x is going to be bigger than u. And similarly, used as we did before, by the Cauchy mean value theorem, so there's going to be this T, or yes, there's going to be this T. There exists a T, an element of x to y, such that, I should say something before that. So for a less than x less than y less than c, there exists a T, so anytime you give me an x and y to satisfy this, there exists a T, and that's an element of x to y, such that f of x minus f of y all over g of x minus g of y is going to be equal to f prime of t over g prime of t, which we know to be greater than u. Okay, now, suppose, again, here we're going to use the hypothesis that the limit as x goes to a of f of x equals to 0 and the limit as x goes to a of g of x equals to 0. Then, when you look at the limit as x goes to a of this quantity, which is f of x minus f of y all over g of x minus g of y. Okay. This quantity is always greater than u, and so here this is equal to, well, first of all, this part as x goes to 0 is equal to, what's left here is f of y over g of y, which is going to be greater than u. So, the limit as y goes to a of f of y over g of y, that's got to be greater than or equal to u, which is greater than w. So, there exists a D element from A to C such that for all x element from A to D, f of x over g of x will be greater than w. And that's what we needed to show, that supposition. Okay? The next supposition, so suppose the limit as x goes to a of g of x equals to infinity. Then, as we had done analogously before, keeping y fixed, and a being less than y, being less than c sub 1, we pick c sub 1 element of a, this is from A to C. Okay? A to C. We pick a c sub 1 element from A to y such that g of x is going to be bigger than g of y. It's going to be bigger than g of y. And g of x is going to be greater than 0. And that's true for all x element from A to C sub 1. Now, since f of x minus f of y over g of x minus g of y, we know that that's greater than u, and that's true for all x element of A to C sub 1, then we have that multiplication, f of x minus f of y over g of x minus g of y times, here I'm going to write down g of x minus g of y all over g of x, and that's going to be greater than u times g of x minus g of y all over g of x, just as we had done in a previous case. I'm sorry, I forgot to turn the camera. Let me take a second here. So here we concluded the previous situation where we were supposing that the limit as x goes to a of f of x equals to 0, and the limit as x goes to a of g of x equals to 0. And so we got what we needed. Okay, now we're supposing that the second part of the hypothesis, this had happened, where the limit as x goes to a of g of x equals to infinity. We're keeping y fixed in between a and c, and we pick c sub 1 in between a and y, such that g of x is greater than g of y. We can do that because x is going towards, g of x is going towards infinity. And g of x is greater than 0. Again, we've got to be able to be positive values for the output value of the function since it's going towards infinity. And that's true for all x in a to c sub 1. And so here, since f of x minus f of y over g of x minus g of y is bigger than u, we know that, for all x. This was true for all x in between a and y. Then this is going to, so it's going to be true for all x between a and c sub 1. If we multiply by this positive quantity, we maintain this inequality. That's what we had. Sorry. So, what we have is that f of x over g of x, just like what we had before, is going to be greater than u minus u times g of y over g of x plus f of y over g of x. Algebraic manipulations. And so the limit as x goes to a of f of x over g of x is going to be greater than, we take the limit of this part, which is going to be u minus u times the limit as x goes to a of g of y over g of x plus the limit as x goes to a of f of y over g of y, I'm sorry, g of x. Where these two limits are zero, so what we get is that the limit is x goes to a of f of x over g of x is got to be bigger than or equal to u, which is bigger than w. So that says there exists a D element from A to C sub 1 such that for all x element from A to D, f of x over g of x has got to be bigger than or equal to u. I'm sorry, it's going to be bigger than w. And so that says that the limit as x goes to a of f of x over g of x equals to infinity. In the last case, I'm not going to go through with very much details. So here, it's case 3. And that's if, or suppose, well, the case is minus infinity is less than a, which is less than infinity. So what I'll say is by similar work, in cases 1 and 2. Okay. For any epsilon greater than 0, we have a D element from A to B, such that A plus epsilon will be less than f of x over g of x, which will be less than a minus epsilon. And this is true for all x element from A to D. And so we will get the limit as x goes to A of f of x over g of x is equal to A. And with this kind of summary of case 3, we will say that concludes the proof. What I want to finish today with is an example where we use L'Hopital's rule. well, maybe we do just a little bit more. But here, as an example, we take the limit as x goes to 0 of e x minus 1 over sine of x. And when we do this, as x goes to 0, e to the x goes towards 1. And then 1 minus 1 goes towards 0. So this goes to 0, and sine of x as x goes to 0 is 0. Okay. So here, we could consider this f of x, e of x minus 1, and g of x is sine x. And so what we notice is that the limit as x goes to 0 of the derivative of this, which is e to the x, over the derivative of this, which is just cosine x, that's equal to, this goes to 1 over 1, so that's just 1. So by L'Hopital's rule, the limit of the original problem, x going to 0, e to the x minus 1 over sine x, it also has to be equal to 1. And in calculus, generally, when we teach calculus, there's a whole section on L'Hopital's rule and variations of indeterminate limit forms where they can be manipulated into 0 over 0, really infinity over infinity, which is a L'Hopital's rule form. Well, I said I would conclude there, but I would like to start just a little bit more of a different topic, or the background for a different topic, to get to the theorem of Taylor's theorem, which we won't do today, but we'll introduce next. Definition of higher order derivatives. So here's a definition. It says if f has derivative f prime on a to b, and if f prime is itself differentiable, we denote the derivative of f prime by f double prime and call f double prime the second derivative of f. Now, we can continue on if f double prime is differentiable. F triple prime, which is equal to the derivative of f double prime, is called the third derivative. Of f. And we can extend this and in general get the following statement. So in general, okay, f superscript n in parentheses is called the nth derivative of f, where the nth derivative of f is really equal to the n minus 1 derivative derivative. And as an example, this is where we'll begin. If we let f of x be equal to x to the fifth plus 6x to the third plus 2x plus 7, then here's what we have. The first derivative is going to be equal to 5x to the fourth. So this is using, if you will, the sum rule, where I take the derivative of each term here. Here I'm using the power rule, where I bring down the power x to 1 less power, plus 18x squared plus 2, and this will be plus 0. And then the second derivative will be equal to 20x to the third plus 16x, that's what I have. The third derivative, so this was the second derivative, the third derivative is equal to 60x squared plus 16. The fourth derivative is equal to 120x, and then the fifth derivative would be equal to 0. I'm sorry, 120. And then we could go on from there. All the derivatives from then on are 0. Okay? And I'll just write that down here. The sixth derivative, well, the nth derivative is equal to 0 where n is greater than or equal to 6. Okay, ladies and gentlemen, that's enough for today. I want to thank you very much for your patience.